Good morning, here we are. It is once again the physics video lecture, Physics 2A video lecture 22. And we're going to start off with some announcements today because we're having some difficulty with the quizzes. And I don't want people to think about quitting yet, okay? I'm working on it from my end. And so there are various options. First of all, I intend to have a good 20 quizzes or so. I want to have at least 20, so 2 to 3 a week eventually. And so the first ones will not really will not carry that much weight. I'm also trying to get some quizzes to the point where everybody can get the problem, just to build up confidence. So for each quiz, there's still going to be 10-minute quizzes, and I'll retain that time. For each quiz, I am announcing what the topic is. I've done it for all 3 quizzes so far, 2 that you've taken, 1 coming up. So I announce the topic so you can prepare for it and have everything lined up, and then just work very carefully. Another thing I can do, eventually we have 20 quizzes, I can drop the first 5. Okay, I can drop a number of them. I can put a lot more points on the later quizzes when people get up to speed. So do not give up and don't become too discouraged. The other thing is the notes and the homework will carry more weight rather than less weight. More weight than was said in the syllabus, because the homework and the notes are very, very important. So keep taking the best possible notes. That's what's building you up. If you take the notes and if you work on your notes. So one more thing before I get started. Working on your notes means repeating what I did using your own thought process. So if you write it down, that's good. But if you can go through it and do it yourself, that's where the real learning takes place. Okay, and even one last thought. I'm seeing many good notes. Okay, so I have confidence that people will be able to improve. Okay, I'm pretty confident we'll be able to improve. I'm going to make some quizzes easy enough that I want everybody to get it, and then we can work our way up. If you have questions and I haven't answered your emails, just write to me again. I'm not ignoring them deliberately. I have a lot of emails to deal with. Okay. And if you have a particular homework problem you'd like dealt with, I'll do it up on the board right here. So without further ado, I'll talk about the horizontal throw. This was the second quiz. Quiz number 2 was the horizontal throw. And I recommended at the time that the easiest way to do it would be using energy conservation, but we can do it a couple of different ways. So what we're looking at is a launch with an initial speed from a height h, and we know it's going to come down and strike at some distance here. Okay, it's going to strike right there. Now what I asked for, I gave V0 and H, I asked for the final speed when it hits. Okay. So the energy method would be to call this point A and this point B and write down EA equals EB. We'll have 1/2 mv0 squared. And if we take this to be our 0, height will have no potential energy there. But that will equal 1/2 mv squared at point B now. Oh, other way around. We're taking the initial potential energy up at the top. Okay. So that's E sub A, and then we have 1/2 mv sub B squared. Okay. So now we've written down the energy conservation law. Masses go away, and we can solve for V. We're going to have 2g, so V squared is 2gh plus V v naught squared, and when I take the square root of that, v0 squared plus 2 times g times h. So here's what you had to arrive at in order to plug in the proper numbers. Yeah, the problem with the computer program on Canvas is it can't give you partial credit. Traditionally, I've graded everything by hand and I give a lot of partial credit. So we're dealing with that, but things will get better. Okay. So that's the horizontal throw with the energy method. The other way to do it, you could have said V final is the square root of Vx squared plus Vy squared. Okay. And then your Vx squared is your V0 squared. Your Vy squared is your minus GT squared. But then you have to figure out how much time it took to fall. Where t is equal to, and I'll show you where it comes from, where 1/2 gt squared is equal to h. That's from the law of free fall, so that t is equal to 2h divided by g square root. So this would be another way to get at the problem, and you can, in retrospect, this way is certainly easier. You should practice both of them. Okay. I could recycle some of these problems, so every quiz problem, make sure you're able to do it, even if you weren't able to do it on the day of the quiz, make sure you're able to master that particular problem. They're all important. Good. So there we have it. And I'll move on into the circular motion discussion, which is a really interesting one. And also regarding the circular motion homework problems, tell me which ones you want me to do. I'll do some of these at the board later. Again, when I have a whole class out in front of me, they turn their homework in every day, and then I immediately do a homework problem on the board. So we can't quite do it that way. Good. So let's start talking about uniform circular motion. The application we're looking at is planetary orbits. So this is going to get really good. Let's start with uniform circular motion. Uniform circular motion, we had a circle of radius r. If we need an orientation, we call counterclockwise the positive orientation. And we have an angle, we have an arc length s, and we have S is equal to r theta, V is equal to r delta theta over delta t. But so for uniform circular motion, by the way, V is constant. And then we have centripetal acceleration, V squared divided by r. Very, very important formula. And the direction of the acceleration is towards the center. So we had a couple homework problems with this. Towards the center of curvature. And then if we have Newton's law in general, then for circular motion, for uniform circular motion, so here's Newton, and then for uniform circular motion, we have F centripetal is equal to m v squared over r, because that's our acceleration. Okay, good. So we had a couple problems assigned. I showed you a couple things, and we'll come back to that when we want to discuss those homework problems. I'm going to move forward to a really nice application. Okay, and this application is the satellite orbit that is taking place very close to the surface of Earth. We're going to call it a near-Earth satellite orbit. And I'll draw some pictures. So, example, near-Earth satellite orbit. Okay. So now we'll sketch the Earth as a big sphere. There's our circle. And the question is, how far away from the surface is a satellite? And the answer is, for example, the space station, it can be that close. Okay, draw a little trajectory. It can actually be seemingly just skimming the surface because the radius of Earth, Mars of Earth, is 6,800 kilometers, and you only have to be a couple hundred kilometers above the surface of Earth to be above all the mountains, obviously, and to be above the atmosphere, because you have to be orbiting with no friction, or let's say negligible friction again. Okay. So the near-Earth orbit's very close, and because of that, the acceleration, which is centripetal acceleration, is really just g. Okay? It's the gravitational acceleration, because we're so close, it's basically 9.8 meters per second. I'm going to put an approximation sign here so I don't get into trouble. What happens is the acceleration becomes smaller and smaller the further away you go from the center of Earth. But at the surface of Earth, it's 9.8, and when you're just a little bit above, it's approximately 9.8. Okay, so you have a near-Earth orbit, and this is really just the horizontal throw, which we just did our quiz on. Under the circumstances that the Earth itself is curving away. So if we were to do a horizontal throw like this, we launch, okay, with V0, then what happens is, here I'll use red, it's like a baseball pitch, right? It eventually hits the ground. But what happens on our blue Earth is that if you throw it fast enough, you match, the trajectory is matching the curvature of the Earth, because the Earth is not flat, okay? And if your trajectory matches the curvature of Earth, the satellite never falls down to the ground. It's always falling, but it's falling around the Earth. Horizontal throw, so right here, satellite falls around Earth, which is the answer to the question, why don't they fall down to the ground? Okay, satellite falls around the Earth. Okay, exclamation point. Yeah, so that's how that works. And since we know about circular motion, we can immediately find out the speed of the orbit. So next, what is the orbital speed? Question mark. Well, we can practically just write it down. I'm going to leave those formulas on the left. Actually, I don't have to do that. So since the satellite's just falling around the Earth, then we have A sub c. I'm just going to write now an equal sign. We know it's a slight approximation. It's g, and that's v squared divided by r, because this time the radius in our formula is the radius of Earth. I'll just leave off the sub e there. R. And so we can solve v near Earth orbit, near Earth, is equal to the square root of r times g. Okay. Let's cross multiply over, take square root, r times g. And if you plug these numbers in, well, I'll go ahead and do it. So you have 6.38 times 10 to the 6 meters times 9.8 meters per second squared. And you know, we can even approximate this. That's 6.4 roughly times 10. Okay, so 60. And we're going to end up with actually roughly 64 times 10 to the 6th, so that would be 8 times 10 to the 3rd. Okay. So we don't even need a calculator for this. Roughly 8 times 10 to the 3rd. I'll write down what your calculator is going to tell you. It's going to tell you roughly 7,900 meters per second. And that's pretty fast. That is pretty fast. That's 5 miles per second. Every time you count 1,001, 1,002, this thing has gotten just about 8 kilometers. Okay. And one more thing. The period of orbit, period capital T of orbit, so that's the time. We'll get that by saying 2 pi, we'll do this. The speed is the distance over the time. Okay, speed is the distance over the time, and that's just the circumference. Therefore, period of orbit is going to be 2 pi radius of Earth divided by v. And I'm just going to write approximately 1.4 hours. You guys go ahead and plug in these numbers here. Radius of Earth, it's there, and figure out how many seconds it is, and then from the seconds you can get to your hours if you need to. It's roughly 5,000 seconds, so it's over an hour, but that's pretty fast to go around the Earth. Good, so that's a nice application of this uniform circular motion. We figured out the satellite speed, and this is an example of something that we've done where we've done everything. We've done everything to get these results during the course of this semester. Okay, now from near-Earth orbits, I want to talk about orbits in general. So satellites around the Earth, the moon around the Earth around the sun, the planets around the sun. So for that, we need to know more than just the law of free fall at Earth. Okay, so this is going to take a little time to build up to it, but what we want to arrive at is Newton's law of gravity, which gives us all of these results very generally. Okay, I'm going to consult the clock here. Excellent. Okay. So next, we will talk about planetary orbits. So first, here's our agenda. Planetary orbits. Isaac Newton. And then universal gravitation. And when we have that, we can then return to planetary and all other orbits. All orbiting bodies, all orbits. Okay. So that is our task. And this takes us all the way back to beginnings of astronomy, trying to discover whether, what are these dots of light in the sky, and are they orbiting the Earth, or is the Earth orbiting them? Okay. So just talking about astronomy for starters, there was a geocentric theory and there was a heliocentric theory. And the geocentric theory said that the heavenly bodies all orbit Earth. So all of the celestial bodies orbit Earth, and it looks like that because we feel that we're stationary and the sun rises and sets and the moon rises and sets and the stars trace out a path across the sky as well. Okay. So that's the reason one could think that celestial bodies orbit Earth. So geocentric means the Earth is at the center. Okay. Earth is at the center. That's what geocentric means. The heliocentric theory, and this is of planetary orbits, is that the sun is at the center. Of planetary orbits, including Earth. This theory here is came to us from classical antiquity. Ptolemy is the astronomer whose name it's associated with. And then in more recent times, the heliocentric theory was proposed by Copernicus. Okay. This is sometime during the 1500s. Look it up. Okay. So the name that comes next, actually I need more board here. So then the heliocentric theory was more firmly established by Kepler, who used the data of Tycho Brahe. So Kepler, all-time great mathematician and astronomer and everything else, he analyzes the data of Tycho Brahe Brahe's data. So astronomical data, and then he comes up with the 3 laws of planetary orbits. Okay, this is obviously a very condensed version of all of this, but we need it. So 3, that's a 3. One more time. That is 3 laws. So the first law is that the orbits of the planets are around the sun. They're not perfect circles, they're ellipses. So planetary orbits are ellipses with the sun at one focus. At one focus. And with any luck, I can bring some materials here. Fantastic. I'm going to demonstrate what an ellipse is according to these concepts here. So these two magnets are going to be the location of the foci, the focuses of this ellipse. And the ellipse is the curve where the sum of the two distances from the foci are equal to a constant. And you can do that just by taking a string here and going around, because these two distances, right, the string being of a constant length, these two distances are always the same. So let's go ahead and draw one. We're going to draw a couple of them. Let's see how high this goes. Yeah, we're going to draw a few of these. I encourage you guys to do this too, with cardboard, whatever you can manage. So here we go. We'll draw an ellipse, and then once we've drawn a couple, we'll label them. So the interesting thing here, it's a beautiful curve, and I'm going to put the location of the focus in each case. Okay. So you'll notice this thing looks pretty oval. The foci are this far apart. So this is our first picture. I'm going to draw a bunch of them. I'll just keep erasing them. So this is a focus, and this is a focus. And Kepler's law says that the sun would be at one of these foci, and the planet would be out here, orbiting. Now watch what happens. Well, actually, before I do that, let's go ahead and label this. So what we do is we say that 2 times A is the distance across the long length of the ellipse. It's called the semi-major axis. And 2 times B is this direction here. So A is the semi-major axis. Semi-major axis. And B is the semi-minor axis. Semi-minor axis. And we have the 2 foci, and I can even label this distance R here. This distance R, as you swing around here, increases. Right? The sun, I'll put a star here, is at one focus. There's nothing at this other focus. Okay, it's just an empty mystery spot. Not a mystery. There's nothing there. Okay. So those are the parameters of the ellipse. Okay. But what I want to show you next, and I might as well send this up. What I want to show you next is what happens when we bring the foci together. As you can imagine, we'll just get a circle. So let's look at that. So we're going to move the foci around. In fact, the next one I do, before I do the circle, I'm going to end with the circle. Before I do the circle, I'm going to put them very, very far apart. So if the foci are this far apart, and I'm not always going to draw where they are, if they are this far apart, the ellipse becomes what we say more and more eccentric. But it's still semi-major axis, semi-minor axis, foci. Okay. And by the way, these will be shown to have astronomical significance, but what we have actually for our Earth, so yeah, make sure you draw these. The situation with the Earth around the sun and the planets is more like this. The foci are very close together, and if I draw this, beautiful. So if I draw this, I have a focus here and another one here. And one of these would represent the sun. In fact, for the orbits of the planets, for the most part, the foci are even relatively closer than in our picture. So you can see that from your point of view, this is just a circle. Okay? It's a circle where the orbital center is slightly off center from the actual one. So you would put the sun here, and then your Earth right there, orbiting. Slightly off center. But just looking at it, it looks like a circle. So the cases, and let's put this as a note right here, planetary orbits are very nearly circular. The thing is, astronomy was already so accurate several hundred years ago, you couldn't just sweep that ellipticity under the rug. You had to acknowledge it. Okay? It was really there. But just from the standpoint of viewing it from a distance, planetary orbits are nearly circular. We're going to make use of that fact. Okay. I'm going to need one more ellipse here. Okay, that's all right. We'll draw another ellipse. So Kepler's second law. We're doing Kepler's law. Second law. Kepler's second. And that is that the radius vector of the orbit, and that's this one right here, sweeps out equal areas in equal times. So I'm just going to write it down and I'll explain it. For the orbiting planet, the radius vector sweeps out equal areas in equal times. So this is the law of areas, sweeps out equal areas in equal times. So for this, we need another ellipse. And since I have my materials here, I'll go ahead and construct one. For the purpose of this law, we're going to make one of the exaggerated ellipses, okay? Because we can really visualize it better. So there's our ellipse. Okay. Once more with feeling. What happened there? Okay, there we go. Oh, I see what happened. Here we go. Okay. Ellipse. There we go. Closes up nicely. And we have. I'm going to ignore the other point. Okay. There's the one where the sun is. So the radius vector is the one that goes from here to the planet. And I'm drawing an area that it sweeps out as the planet orbits counterclockwise, okay? So it is sweeping out that area that I will draw in red here. Is the area. So it says equal areas and equal times. So on the far side of the orbit, anywhere really, but if we do the far side, we need to get an equal area to my red area there, so it has to be much narrower. So here, provided I did that right, okay, I could make it a little wider. But yeah, equal areas in equal times, and that of course means that it's going much faster when it's close to the sun and much slower when it's further away. And then in our real planetary orbits, of course, it's true as well, but it's much more subtle. It's much more subtle than that picture. So equal areas and equal times. That's the law of areas. And Kepler's third law is called the law of periods. Yeah, we have everything up here. Periods. So for all planets, and back then he knew the planets out to Saturn or Jupiter, I think. Okay, so he had a half a dozen planets. or 4 or 5. So the law of periods, so for all planets in the solar system, t squared divided by a cubed is equal to a constant. In other words, the period, the orbital time, the time it takes to go around, the orbital period squared divided by the semi-major axis cubed, right? For every planet, it's the same constant. So, same constant, comma, all planets. Same constant, all planets. So this is very, very important. This is the one we're going to use along with Isaac Newton later on. So those are Kepler's 3 laws. Physics had not yet really been invented, so they were done, they were obtained just from astronomical data. Okay. See how we're doing time-wise. Radius vectors, supersonic polarity, and equal time. So yeah, that's all 3 of those. And I should even make a further note here. We can also say, because we have very nearly circular orbits, we can also say t squared divided by r cubed is approximately equal to a constant. Okay, because for our planetary orbits, the semi-major axis A and the radius r are very, very close. Very close. Good. So that's an approximation here. Okay, we have Kepler's 3 laws. This one we're going to hold on to because we're going to make use of. And actually, this is kind of stuff that would be great for you guys to read up on. Tycho Brahe was an astronomer up in Denmark, of all places. And all of his observations were still done with the naked eye. The telescope had not yet been invented and applied to astronomy. So these were all done with the naked eye, but he had large instruments, large instruments to measure angles, things like that. And his data were so accurate, they were the best that anyone had. And so when Kepler analyzed them, he could no longer just pretend it's a circle. That's one way to look at it. He was forced by the data and his innate scientific honesty to acknowledge the lack of circularity, that it's actually like like an ellipse. And he then actually found this law that they're ellipses, okay, and the other 2 laws as well. So yeah, it's one of the great moments of all time. Okay, so we're going to do that at much time, but yeah, we can do this. So what I'll do is talk about how Isaac Newton used his ideas of physics and Kepler's laws in order to discover the universal gravitation law. And then next time we'll pick up and start doing the calculations with it. We should be able to get a couple homework problems out of what we've done so far. Anyway, so now we have Newton. And the story with him sitting under the tree is so good that we'll actually place him under a tree, and he's here with his big wig, reading a book. Okay. And at the same time, there is a moon in the sky. Okay. There's some kind of moon. So moon, Newton, apple. Okay. I should be using red. So the significance of this story is that Newton had the idea that the laws governing the fall of the apple, which is just the law of free fall, is actually the same law governing the motion of the moon. So that's why this is a good thing to remember. So laws of free fall, so that's the apple, are the same as the laws of orbits, which represents the moon. Laws of orbits. Okay. So that's the idea. This is the idea here that Newton had. The laws that govern the fall of the apple are the same laws that govern the orbits of the planets and the moon and everything else. Okay. So we've already learned about free fall. We know it's a force law, right? And the force law is the weight of the apple. So what he's saying is, yeah, I don't have to explicate that. I've said it. Laws of free fall, F equals MA, where A is equal to G, we could say that, right? That's the law of free fall right there. It's going to be the same as the law of the orbit. That's proved here. So what we're going to do is draw an orbiting object that's orbiting a central body. So what we do is we consider a circular orbit, and we'll call this M1 and this M2, right? And the radius of the orbit is R. And now the question is, what is the force law going to be in this scenario? Circular orbit. What is the force law going to be? Question mark. So we have all the ingredients to go through the thought process. What the force law is going to be, right? We just said this is the force law here for the falling apple, for free fall, for projectile motion. What's the force law for a planet? So here goes. The force law. The force between M1 and M2. So we have 3 points to be made. The first point is that the force will be proportional to M1, just like in free fall, right? Just like in free fall, the force is proportional to M1. So just like in free fall. However, the next point is that the force must also be proportional to M2. And that's just the reciprocal nature of Newton's third law, okay? Because you just have to take the standpoint of M2 instead of M1. And so by Newton's third law, if it's proportional to M1, it also has to be proportional to M2. And then the third point is because it's a circular orbit, the force is equal to M1 v squared over R, Or I could also just say the force is proportional to v squared over r, okay? But yeah, now we're thinking we're orbiting a large central body. So we can go ahead and write it this way. Now watch this. Now we're going to treat it as a circular orbit, uniform circular motion, so the v, as we saw earlier, is 2 pi r over t, can be squared. So I have mv squared, and I have 1 divided by r. So now let's just multiply these out. We've got m1, we've got 4 pi squared, we've got r squared. In the denominator, we have t squared times r. And our last step is to remember that t squared is proportional to r cubed, right? That's Kepler's third law. Kepler, okay, t squared is proportional to r cubed. So if we get rid of the mass in 4 pi here, what do we have? We have r squared over r cubed times r. So that's r squared over r to the 4th, that's 1 over r squared. So the result, the force between two objects that can orbit each other, but just in general, the force between two objects is proportional to the product of the masses and inversely proportional to the separation distance squared. So this is the famous inverse square law. And I've just shown you how it was arrived at. Next time I'm going to talk about all the ramifications. This is huge. Okay? This is the famous inverse square law. And again, we've done really every step we needed to. Obviously, we just had to learn about Kepler's laws. But otherwise, we've just been able to follow the thought process all the way to here. Okay, I'm checking the time once more. And good. Let's see if we can get some homework on this subject. This is all background, so exactly this, not yet. But we're in chapter 7, and I think we'll do just another uniform circular motion type of problem. For the law of gravity, I need another lecture, and we'll do that. You know what, I'm just going to add one more problem. So this is homework number, what are we on, 21 or 22? 22. Chapter 7, problem. Let's see here, make a little more room. Problem 65. This is really just another version of the roller coaster problem. And at some point I'm going to do some of these problems at the board, but this is just to stay in practice. What we're going to do next time, next lecture, will be all about the circular orbits and Newton's law of gravity. There's quite a bit to do there. Good. See you guys next time.